In section 7, we're going to be looking at applications of the line. One specifically is called the rate of change, or the average rate of change. And we're going to be using lines to help us to illustrate what this average rate of change concept looks like visually. So example 7.1 is going to take us through a series of steps that will eventually lead us to the concept of average rate of change. So for example 7.1, it's giving us a function f, and f is defined over all real numbers using the equation f of x equals x minus 3 squared. I would ask that at this point you get ready to pause the video and graph this for yourself. This should be something that you can graph using a parent function and transformation graphing technique, and you would want to recognize your parent function and the transformation and perform your graph. So hopefully you've completed your graph already on the f of x here, and what you should see is a squaring function that's been shifted to the right by 3. So let me try to get mine here, and it looks something like this. And the part B, we can put arrows on this if we want, arrows there. Part B says find f of 1, f of 3, f of 4, and f of 6, and use these function values to mark 4 points on the graph of f. So we can use these as a means to check to see does our graph actually fit what we were expecting it to be. So the easiest thing here would be probably just to think of this from a table perspective. That'd be a good way to organize our work here. We'll have x, f of x, and I'll put 1, 3, 4, and 6. So over here in the margin we can do the calculations. F of 1, and we'll have 1 minus 3 squared, negative 2 squared, which is 4. And I'll write down 1, 4. So that means there should be a point located at 1, 4, and there is. So I'll mark it there in red. We'll do the same thing with an x value of 3, f of 3. 3 minus 3 squared will be 0 squared, which is 0. So I should have a point at 3, 0, and I do, which represents my relative minimum. On to f of 4. 4 minus 3 squared will be 1 squared, which is 1. So we'll have 4, 1, and yep, we have a point there at 4, 1. And the last point that I'm looking for, f of 6. 6 minus 3 squared will be 3 squared, giving us 9. So 6, 9. Now this one I didn't already have here because I only drew a portion of the parabola that I'm used to drawing. So let me go ahead and erase these arrows and put a point at 6, 9. And I'll put another point over here at 0, 9. And then that'll complete the parabola shape over that whole window. So that's a more accurate picture of f. And let me go back and mark the point at 6, 9. There we go. So that's part B. Part B is just looking for some function values. Part C says draw a secant line between x equals 1 and x equals 3. So a secant line is just a line that ends up crossing 2 points on a function. So we have our function here, which is the parabola shape, and we already have the point marked that goes with x equals 1 and x equals 3. So all we have to do is just connect the dots with a straight line. So straight line-ish, sort of straight, right there. And I'm going to call that line 1. because I'm also asked to draw another line, draw a secant line between x equals 4 and x equals 6. So I'm going to attempt to draw a straight line there as well. And I'll call that line 2. So now it says in part D, find the slope of each secant line from part C. So when I think about slope, I think about the calculation y2 minus y1 divided by x2 minus x1. And it's a perfectly good way to think about slope. And I should be able to do that for the first line. We'll call it M1. M1 will be the first slope of the first line. So doing this calculation, and we're going to need to identify what's the first point, what's the second point. We have, I'll call the first point for line 1 the point at 1 comma 4, and then my second point, I'll call that the point at 3 comma 0. So that gives me my x1 y1 and the x2 y2. So I substitute those values in. That'll be 0 minus 4 all divided by 3 minus 1. So that's negative 4 over 2, which ends up giving us negative 2. So that's the slope of L1, which is one of our secant lines. And I can do the same thing for M2. M2 will also be a y2 minus y1 over x2 minus x1 calculation, but I won't be using the same ordered pairs. Obviously, I'll be using a different set. So let me erase the ones that I have here and see if I can clean this up just a bit. There we go. So the ordered pair that I'm going to use here are 4 comma 1 and 6 comma 9. So I'm going to use the 4 comma 1 as my x1 and y1. 6, 9 will be my x2 and y2. So my M2 calculation will be 9 minus 1 over 6 minus 4, giving me 8 over 2, and we would simplify that and call it 4. Now, as it turns out, the slope of a secant line is also known as the average rate of change. So right here where it says slope of secant line, this is also known as average rate of change. Definition 7.1 is going to officially define the average rate of change for us, and so I will encourage you to be looking at your example 7.1 while you're looking at the definition for average rate of change.